normal basis vector. Okay, these three vectors are orthonormal basis vectors. So here is a complete the solution of this question. Next question. Question 1c. Find the eigenvalues and the basis for the eigenspace of a raised to 25 and a plus 2i. Okay, where a is equal to 3 0 8 minus 1. Here is a 2 cross 2 matrix. The first row is 3 0 and the second row is 8 minus 1. This question asked in 3 marks. So just try to understand, we have to find eigenvalue and eigen basis for the eigenspace for a raised to 25 and a plus 2i. Okay, not for a. So here we use one important theorem after some simplification. So first we find eigenvalues and eigenvectors of the matrix A, right? So for that definitely we have to find eigenvalue and eigenvector for the basis given matrix A. So the characteristic equation of A is determinant of A minus lambda I, that is equal to 0, right? And the determinant is 3 minus lambda 0 8 minus 1 minus lambda, that is equal to 0. When we simplify this determinant, we get 3 minus lambda into minus 1 minus lambda is equal to 0. So the eigenvalues of A are lambda is equal to minus 1 and 3. Lambda is equal to minus 1 and 3. Okay, and now directly you can also see that the eigenvalues of A is 3 and minus 1, because this is a lower triangular matrix. You can see except the main diagonal, all the elements means only we get one element, right? So except the main diagonal and below that elements, all the elements are 0. So this is actually lower triangular matrix, that you can understand by the definition of lower triangular matrix. And in lower triangular matrix or upper triangular matrix, only the main diagonal entries, only the main diagonal elements are the eigenvalue. Okay, and here is the eigenvalue is 3 minus 1, that is exactly the main diagonal elements, right? Now for lambda is equal to minus 1, the matrix equation A minus lambda I into x, that is equal to 0. Put lambda is equal to minus 1 in the matrix. In this equation we get A plus I into x, that is equal to 0. Okay, what is our A? A is 3 0 8 minus 1 plus I means 1 0 0 1, identity matrix. So when you add these two matrices, 3 0 8 minus 1 plus 1 0 0 1, we get 4 0 8 0. Okay, 4 0 8 0. So here is the matrix 4 0 8 0 to x1 x2, that is equal to 0 0. So to solve these equations, 4x1 is equal to 0, 8x1 is equal to 0, but x2 is a free variable, right? So that's why we take x2 is equal to k, and the eigenvector corresponding to lambda is equal to minus 1 is 0 1, correct? Because x1 is 0 and x2 is equal to k, so k will be common, and the eigenvector corresponding to lambda is equal to minus 1 is 0 1. Now we want to find the eigenvector corresponding to lambda is equal to 3. So for lambda is equal to 3, the matrix equation A minus 3i into x, that is equal to 0. Okay, and when we put A is, what is A? 3 0 8 minus 1 minus 3i, that means 3 0 0 3. So 3 minus 3 0, 0 minus 0 0, 8 minus 0 8. Okay, and minus 1 minus 3, that is minus 4. So the first row becomes 0 0 and the second row become 8 minus 4. Okay, So that's why here the matrix 0 0 8 minus 4 into x1 x2, that is equal to 0 0. To solve this equation, we get 8x1 minus 4x2, that is equal to 0, right? Using this matrix equation, we get the linear equation, that is 8x1 minus 4x2, that is equal to 0. Okay, hence 2x1, that is equal to x2, 4 will be common, so hence 2x1, that is equal to x2. Now taking x1 is equal to 1, taking x1 is equal to 1, we get x2 is equal to 2, correct? So the eigenvector corresponding to lambda is equal to 3 is 1 2. Now actually we have to find the eigenvector and eigen basis for the eigenspace is not for a raised to 25 and a plus 2i. So that's why we have to use this important result, this important theorem. Now we have already the eigenvector and eigenvalue for the given matrix A, right? Just try to understand the question properly. We already find the eigenvector and eigenvalue for the given matrix A, right? And we want to basically we want to find the eigenvector and eigenvalue for the matrix A raised to 25 and a plus 2i. So that's why we use this theorem. Just try to understand the statement of this theorem. See, if the eigenvalues of A are lambda 1, lambda 2 up to lambda n, then the eigenvalues of A raised to k are lambda 1 raised to k, lambda 2 raised to k up to lambda n raised to k, right? And each eigenvector of A is still an eigenvector of A raised to k. So first of all we want to find the eigenvalue and eigenvector of A raised to 25. So using the above result, now you can understand, we can say that the basis vector are definitely same, right? Because you can see each eigenvector of A is still an eigenvector of A raised to k. So the basis vector, right, are same. Using the above result, we can say that the basis for the given space of A raised to 25 is still 0 1 and 1 2. That is exactly the basis vector for the basis vector for the given matrix A. Now what is our eigenvalue of and eigenvalue of A raised to 25? Here is a just correction, and the eigenvalue of A raised to 25 are minus 1 raised to 25 and 3 raised to 25, right? Just we have to take a degree of the eigenvalue of the given matrix A, right? So here is we find eigenvector and eigenvalue of A raised to 25. Next we want to find eigenvector and eigenvalue of A plus 2i. So here is one another result. Also, if the eigenvalues of A are lambda 1, lambda 2 up to lambda n, then the eigenvalue of A plus ki are lambda 1 plus k, lambda 2 plus k up to lambda n plus k, right? So we want to find the eigenvalue of A plus 2i. So k is equal to 2, right? K is equal to 2, correct? So and we eigenvalue of A is minus 1 3. So that's why eigenvalue of A plus 2i is minus 1 plus 2. You can see minus 1 plus 2 and 3 plus 2. That means what, 1 and 5 are eigenvalue of A plus 2i. Okay, and eigenvector of A is still an eigenvector of A plus ki. So again the eigenvector are same, 0 1 and 1 2 are also the eigenvector of A plus 2i. Okay, so here is a complete the solution of this question. Next question. Question 1D. First part, show that the function f of x is equal to x and g of x is equal to sin x form a linearly independent set of vectors in this set of continuous function from minus infinite to infinite. This question asked just in 1 marks. Here we use Wronskian determinant, right? The Wronskian for two function f of x and g of x is defined as the first row is f of x g of x, and this is second row f dash x g dash x. So the derivative of these two functions for the given functions. So the Wronskian determinant, that is equal to x sin x. The derivative of x is 1, the derivative of sin x is cos x, just simplify this determinant, that is x cos x minus sin x, right? This function does not have value 0 for all x in the interval minus infinite to infinite. Okay, so f1 and f2 form a linearly independent set in C1 from minus infinite to infinite. So here the complete the solution of this question. Next question, question 1D, the second part. Show that if 0 less than theta less than pi, then A is equal to cos theta minus sin theta cos theta has no real eigen values and consequently no eigen vectors. Okay, no real eigen values of this matrix where theta is between 0 to pi, that we have to prove. So the characteristic equation of A is determinant of A minus lambda I, that is equal to 0. So first of all solve this equation, put the value of A, that is cos theta, and minus lambda I, that means in only the main diagonal entries we have to add minus lambda. So cos theta minus lambda minus sin theta and cos theta minus lambda, that is equal to 0. So the cos theta minus lambda square plus sin square theta, that is equal to 0. Okay, cos square theta, simplify these equations, cos square theta minus 2 lambda cos theta plus lambda square plus sin square theta, that is equal to 0. Okay, so and now cos square theta plus sin square theta, that is equal to 1, that we know. So again simplify this equation, just rewrite this equation with the first term is lambda square, second term is this term minus 2 lambda cos theta, and the last one is cos square theta plus sin square theta is 1, so plus 1 is equal to 0, right? So this is now our quadratic equation to find lambda. This is a quadratic equation in lambda. Delta is equal to b square minus 4ac, right? That we know. Okay, so b means what is b? The coefficient of lambda in the second term, middle term, that is minus 2 cos lambda. So minus 2 cos lambda square minus 4. What is our a? A is 1, the coefficient of lambda square, and c is a constant part, that is also 1. So minus 4 a c, that is minus 4. So 4 cos square theta minus 4, we get 4 cos square theta minus 4. 4 will be common, cos square theta minus 1, and cos square theta minus 1 we get minus sin square theta. So that's why the delta is equal to minus sin square theta, minus 4 sin square theta, that is always less than 0. Okay, this part is always less than 0. So clearly the root of equation 1 are not real. So the matrix A has no real eigen values and consequently no eigen vectors. Okay, so here is a complete the question 1. Next question, question 2. Okay, sorry, here is a one remaining part, question 1D, the third part. Define a singular matrix, find the inverse of the matrix A if it is invertible. A is equal to 1 0 1 minus 1 1 minus 1, and the third row is 0 1 0. This question asked in 1 marks again. So what is the meaning of singular matrix? A matrix A is said to be singular if determinant of A is 0, right? Determinant of A is equal to 0. Those matrix is called singular matrix. Now find the inverse of the given matrix if it is invertible. So first of all we have to check that the given matrix is invertible or not. That means can we find the inverse of this matrix or not? Okay, so if determinant is equal to 0, definitely it is a singular matrix and we cannot find the inverse of the given matrix. Okay, the inverse of the given matrix does not exist if determinant of A is equal to 0. So for the given matrix A, here is the determinant 1 0 1 minus 1 1 minus 1 0 1 0, right? Just using some row operations, right? We multiply first row with 1 and add into the second row. So that's why 1 0 1 0 1 0 and 0 1 0. Now Directly you can also find the determinant of this matrix, that is no problem, right? So determinant of this matrix is equal to 0, that just check it. Okay, clearly the determinant of this matrix is equal to 0. So the inverse of this matrix does not exist. Okay, next question, question 2. So the first question is asked in 14 marks and it is a compulsory question. The next question, question 2. Determine the dimension and the basis for the solution space of the system 3x1 plus x2 plus x3 plus x4 is equal to 0, 5x1 minus x2 plus x3 minus x4 is equal to 0. So the matrix equation for the given system is 3 1 1. You can see from the first matrix, right? From the first matrix 3 1 1 1 5, and the second row is from coming from the second matrix, second equation 5 minus 1 1 minus 1 into x1 x2 x3 x4, that is equal to 0 0. So ax is equal to 0. Say here a is equal to 3 1 1 1, b is and the second row is 5 minus 1 1 minus 1. Okay, now using some row operations we have to convert the matrix into a row echelon form. So first of all we dividing first row by 3, right? So we get 1 1 by 3 1 by 3 1 by 3. The second row is as it is 5 minus 1 1 minus 1. Okay, now we have to convert the given matrix into a row echelon form. So that's why we multiply first row with minus 5 and add into the second row. 1 1 by 3 1 by 3 1 by 3, the first row is as it is. Second row become now coming from this equation, you can see 5 minus 5 0, minus 1 minus 5 by 3, so that is minus 8 by 3. Again 1 minus 5 by 3, so that is 3 minus 5 minus 2 by 3, and minus 1 minus 5 by 3, that is minus 8 by 3. So here